How do you find exoplanets? This task is far from being easy. In fact, there are many head-scratching obstacles astronomers have to deal with. For example, how do you detect a planet-sized astronomical object orbiting a star dozens of light years away? The complexity of the task becomes clear if we consider that even stars appear as nothing more than pinpoints of light when viewed with even the largest telescopes. Planets do not emit light of their own, but are merely illuminated by the stars they orbit. As a result, planets are very small and very dark compared to stars, which in itself would make them very difficult to detect from Earth. Add to that the fact that these inconspicuous objects are inevitably found right next to the stars they orbit, and the task of observing them becomes, well, nigh impossible. Astronomers, however, are nothing if not ingenious. Since the planets cannot be observed directly, the planet hunters decided to observe stars instead, and look for the minute effects that orbiting planets have upon them. Astronomers have been looking for some of these since the dawn of the 20th century, but only in the past 10 years, instruments have become sensitive enough to finally detect them without ambiguity. There are different approaches used. Each approach has its strengths and weaknesses. Transit photometry. A solar eclipse is one of the coolest astronomical events you'll ever experience. It happens when the moon passes directly in front of the sun, blocking its light. This is similar to how the transit method finds exoplanets. When a planet passes directly between an observer and the star it orbits, it blocks some of the star's light, and these events are called transits. For a brief period of time, the star actually gets dimmer. It's a tiny change, but it's enough to clue astronomers into the presence of an exoplanet around a distant star. The size and length of a transit can tell us a lot about the planet and what's causing the transit. Bigger planets block more light, so they create deeper light curves. Also, the farther away a planet is, the longer it takes to orbit and pass in front of its star. So the longer a transit event lasts, the farther away that planet is from its star. Radial velocity. The radial velocity method is the most effective method for locating exoplanets with existing technology. Although their approaches hold great promise for the future, the vast majority of exoplanets discovered so far were detected by this method. The radial velocity method relies on the fact that a star does not remain completely stationary when it is orbited by a planet. It moves ever so slightly in a small circle or ellipse, responding to the gravitational tug of its smaller companion. When viewed from a distance, these slight movements affect the star's normal light spectrum or colour signature. If the star is moving towards the observer, then its spectrum would appear slightly shifted towards the blue. If it is moving away, it will be shifted towards the red. Using highly sensitive spectrographs, the scientists on Earth can track a star's spectrum, searching for periodic shifts towards the red, blue, and back again. If the shifts are regular, happening on fixed intervals of time, it means that the observed star is moving slightly back and forth towards the Earth. This indicates that the observed star is certainly being orbited by a planet that is causing the wobbling effect. Direct imaging. Exoplanets are far away, and they are millions of times dimmer than the stars they orbit, so unsurprisingly, taking pictures of them the same way you take pictures of, say, Jupiter or Venus, is exceedingly hard. New techniques and rapidly advancing technologies are making it happen. The major problem astronomers face in trying to directly image exoplanets is that the stars they orbit are millions of times brighter than their planets. Any light reflected off the planet or heat radiation from the planet itself is drowned out by the massive amounts of radiation coming from its host star. It's like trying to find a flea in a light bulb or a firefly flitting around a spotlight. On a bright day, you might use a pair of sunglasses or a car's sun visor, or maybe just your hand to block the glare of the sun so you can see other things. This is the same principle behind the instruments designed to directly image exoplanets. They use various techniques to block out the light of stars that might have planets orbiting them. Once the glare of the star is reduced, they can get a better look at objects around the star that might be exoplanets. MICROLENSING. When a distant star or quasar gets sufficiently aligned with a massive compact foreground object, the bending of light due to its gravitational field, as discussed by Einstein in 1915, lends to two distorted, unresolved images, resulting in an observable magnification. The timescale of the transient brightening depends on the mass of the foreground object, as well as on relative proper motion between the background source and the foreground lens object. Since microlensing observations do not rely on radiation received from the lens object, this effect, therefore, allows astronomers to study massive objects no matter how faint. It is thus an ideal technique to study the galactic population of such faint or dark objects like brown dwarfs, red dwarfs, planets, white dwarfs, neutron stars, black holes, and massive compact halo objects.